At the center of every black hole, the laws of physics commit suicide. Information vanishes, causality shatters, reality itself collapses into contradiction. This is not speculation. This is what the equations tell us, and physicists have spent 50 years trying to prove the equations wrong. They have failed. The paradoxes remain, unresolved, multiplying, infecting every corner of modern science. From quantum mechanics to cosmology, from the beginning of time to its end, our most trusted theories are screaming at each other, each claiming the other is impossible. These are not puzzles waiting for clever solutions. These are cracks in the foundation of reality, and they are growing. If you want to see how close physics is to collapse, hit that like button and subscribe, because what follows will shake everything you thought was solid. Prepare yourselves. We begin. When Stephen Hawking discovered that black holes evaporate, he accidentally proved that the universe makes no sense. The year was 1974. Hawking applied quantum mechanics to the curved space-time around a black hole's event horizon and found something no one expected. Black holes are not perfectly black. They radiate. They glow with thermal energy, slowly losing mass until they vanish completely. This was revolutionary. It earned Hawking legendary status. But it also created a problem that has tortured physicists for half a century. Here is the conflict. Quantum mechanics has one absolute rule. Information cannot be destroyed. Every particle, every interaction, every quantum state leaves a permanent mark on the universe. You can scramble information, hide it, spread it across 1 billion light years, but you cannot erase it. The mathematics of quantum theory demands this. Without information preservation, the equations break down. Probability stops working, cause and effect dissolve. The universe becomes incoherent. General relativity has a different rule. Anything that crosses a black hole's event horizon is gone. Not hidden, not scrambled, gone. The event horizon is a one-way membrane. Matter falls in, light falls in, information falls in, nothing comes out. Inside the horizon, space-time curves so violently that all paths lead inward to the singularity, a point where density becomes infinite and physics stops making predictions. Whatever falls into that singularity is crushed out of existence. No records remain, no information survives. These two rules cannot both be true. If quantum mechanics is correct, black holes must preserve information somehow. If general relativity is correct, information is annihilated at the singularity. One of these theories, both tested to extraordinary precision in every other context, must be fundamentally wrong. Hawking radiation makes the paradox worse. When a black hole radiates, it emits particles that appear to be completely random. Thermal radiation carries no information about what fell into the black hole. A black hole that swallowed a library and a black hole that swallowed an equivalent mass of hydrogen gas radiate identically. The outgoing radiation is a perfect thermal glow determined only by the black hole's mass, spin, and charge. This is called the no-hair theorem. Black holes have no memory, no hair, no distinguishing features beyond those three numbers. So where did the information go? The library contained trillions of bits of data, specific arrangements of atoms encoding specific words and ideas. That information entered the black hole. It cannot simply vanish. Quantum mechanics forbids it. But the Hawking radiation coming out contains none of it. The radiation is generic, structureless, random. The information is not encoded in the outgoing particles. It is not imprinted on the event horizon. It is not hiding in the black hole's interior because eventually the black hole evaporates completely, leaving only that random radiation. Physicists call this the information paradox. It sounds abstract. It is not. This paradox strikes at the heart of predictability itself. If information can be destroyed, the universe is not deterministic. You cannot reconstruct the past from the present. You cannot predict the future from initial conditions. The entire framework of physics collapses. Every equation we write assumes information preservation. Lose that, and you lose everything. Hawking himself believed information was destroyed. He argued that quantum mechanics must be modified near black holes, that information loss is real, and we need to accept it. This position horrified most physicists. It meant abandoning the foundation of quantum theory, the most successful scientific theory ever created. For 30 years, the debate raged. Hawking versus the quantum establishment. No resolution, no compromise. Then the holographic principle emerged. This idea, developed by Gerard 't Hooft and Leonard Susskind in the 1990s, proposed something radical. Information is not stored in the black hole's volume. It is encoded on the event horizon's surface. The horizon acts like a hologram, a two-dimensional surface containing all the information about the three-dimensional interior. When the black hole evaporates, the information is released in subtle correlations within the Hawking radiation. It is scrambled beyond recognition, but it exists. Information is preserved. This sounds like a solution. It is not. The holographic principle creates new paradoxes. If information is encoded on the horizon, an observer falling into the black hole should see it imprinted there. But general relativity says the horizon is smooth and featureless. An infalling observer crosses it without noticing anything special. This is the equivalence principle, another foundation of physics. You cannot feel gravity in free fall. The horizon should be unremarkable, but if information is encoded there, the horizon must be a violent place. A firewall of high-energy particles incinerating anything that approaches. This firewall paradox emerged in 2012. 4 physicists, Ahmed Almeri, Donald Marolf, Joseph Polchinski, and James Sully, proved that you cannot have both a smooth horizon and information preservation. One must go. Either the equivalence principle is wrong, meaning general relativity fails at horizons, or information is destroyed, meaning quantum mechanics fails at horizons. Pick your poison. Hawking eventually conceded. In 2004, he reversed his position and agreed that information is preserved, though he never explained how. He simply accepted that the paradox demanded it. But conceding information preservation does not solve the paradox, it just shifts the problem. How is the information encoded? How does it escape? The mathematics remains incomplete. The mechanism remains unknown. Some physicists propose that black holes are not what we think. They suggest the singularity does not exist. Space-time might form a new structure at the center, a Planck star or a wormhole or a region of quantum foam. These exotic structures could store information and release it later, but we have no theory of quantum gravity to describe these objects. We are guessing. Others propose that the event horizon itself is an illusion. The apparent horizon might be a temporary surface that eventually dissolves, releasing information as the black hole evaporates. But this requires information to remain near the horizon for billions of years, hovering just outside while the black hole slowly shrinks. The mathematics of this scenario barely holds together. The paradox remains unsolved. Every proposed solution breaks something else. Save quantum mechanics and you destroy general relativity. Save general relativity and you destroy quantum mechanics. Invent new physics and you have no evidence for it, no way to test it, no reason to believe it beyond desperation. Black holes are real. Thousands have been observed. Hawking radiation is theoretically solid. Quantum mechanics is experimentally verified. General relativity is tested to incredible precision. All of this is true. All of this is incompatible. Therefore, we do not understand reality. Somewhere in the fabric of space-time and quantum fields, something is deeply wrong. The information paradox is not a puzzle waiting for a clever trick. It is a symptom of a broken framework. Physics is incomplete. The theories we use every day, the theories that built the modern world, are approximations that fail at black holes. And black holes are not exotic curiosities. They are common. Millions exist in our galaxy alone. The paradox is not theoretical. It is sitting out there in space, happening right now, mocking us. But this is only the beginning. Another paradox waits in the quantum realm, and it is even stranger. Quantum mechanics tells us that particles exist in multiple states simultaneously until observed. This is not interpretation. This is what the mathematics demands. An electron does not have a definite position or momentum until you measure it. Before measurement, it exists in superposition, occupying all possible states at once. The wave function describes this superposition mathematically, assigning probabilities to each possible outcome. Then you perform a measurement. The wave function collapses. All possibilities vanish except one. The electron appears in a single definite state. This collapse happens instantaneously, everywhere the wave function exists, which can be spread across vast distances. This is the measurement problem, and it has haunted physics for a century. The problem is simple. Quantum mechanics provides 2 completely different rules for how systems evolve. Rule 1 applies when no one is looking. The wave function evolves smoothly according to the Schrödinger equation. Superposition grows. Quantum interference creates complex patterns. Everything is deterministic and reversible. Rule 2 applies during measurement. The wave function collapses randomly. Superposition vanishes. One outcome becomes real. The process is instantaneous and irreversible. These rules contradict each other. You cannot derive Rule 2 from Rule 1. They are fundamentally incompatible descriptions of reality. The question that no one can answer is what counts as a measurement. When exactly does the wave function collapse? If you send a photon through a double slit, it behaves like a wave, interfering with itself and creating a pattern on a screen. The photon travels through both slits simultaneously in superposition. But if you place a detector at one slit to check which path the photon takes, the interference pattern disappears. The photon behaves like a particle, going through one slit or the other. The act of measurement destroys the superposition. But what is special about the detector? The detector is made of atoms. Those atoms are made of particles obeying quantum mechanics. Why does the detector cause collapse when it is itself a quantum system? You could describe the detector quantum mechanically. Before it interacts with the photon, it is in a superposition of ready states. After interaction, it becomes entangled with the photon. Now the combined system is in superposition. Detector shows left and photon went left, or detector shows right and photon went right. No collapse has occurred. Superposition has simply spread to include the detector. You could add more layers. The detector sends a signal to a computer. The computer records the result. A scientist reads the computer screen. At each stage, you can describe the entire system quantum mechanically. The superposition grows to include the computer, then the scientist, then the laboratory, then the entire universe. At no point does the mathematics demand collapse. The Schrödinger equation never stops applying. Superposition never ends. Yet we only ever see one outcome. We never observe superposition at the macroscopic scale. Cats are not simultaneously alive and dead. Scientists do not exist in superposition of having seen different results. This is Schrödinger's cat, proposed in 1935 not as a curiosity but as a weapon. Erwin Schrödinger was attacking the Copenhagen interpretation of quantum mechanics, the standard view that measurement causes collapse. He designed the thought experiment to show how absurd this view becomes when applied to everyday objects. Place a cat in a box with a vial of poison connected to a radioactive atom. If the atom decays, the poison releases and the cat dies. If the atom does not decay, the cat lives. Quantum mechanics says the atom is in superposition of decayed and not decayed until observed. Therefore, the cat is in superposition of alive and dead until you open the box. Schrödinger intended this as a reductio ad absurdum. Surely cats are not in superposition. Therefore, something is wrong with the Copenhagen interpretation. Nearly 90 years later, the problem remains unsolved. Physicists have proposed dozens of interpretations, each trying to explain what happens during measurement. None are satisfactory. The Copenhagen interpretation simply declares that measurement causes collapse without explaining what measurement means or how collapse happens. It works pragmatically. Shut up and calculate. But it offers no mechanism, no deeper understanding. It places an arbitrary boundary between quantum and classical worlds without justifying where that boundary lies. The many worlds interpretation eliminates collapse entirely. Every quantum event causes the universe to split into multiple branches. In one branch, the atom decays and the cat dies. In another branch, the atom does not decay and the cat lives. Both outcomes are real. Both universes exist. You only perceive one because your consciousness exists in one branch. Measurement does not collapse the wave function. It entangles you with the system, placing different versions of you in different branches. This interpretation is mathematically elegant. It requires no modification to quantum mechanics, but it demands that countless parallel universes exist, forever splitting at every quantum event. Most of these universes are unreachable and unobservable. The ontological cost is staggering. Pilot wave theory restores determinism by adding hidden variables. Particles have definite positions at all times, guided by a quantum wave that evolves according to the Schrödinger equation. Measurement reveals the particle's pre-existing position rather than creating it. This eliminates superposition for particles while keeping it for the guiding wave. The theory reproduces quantum predictions exactly, but it requires instantaneous non-local influences. The pilot wave responds immediately to changes anywhere in the system, violating the spirit if not the letter of relativity. And it doubles the ontology. Reality contains both particles and waves. both following their own rules. Objective collapse theories modify the Schrödinger equation itself. They add nonlinear terms that cause spontaneous collapse when systems reach a certain size or complexity. Small systems like electrons remain in superposition. Large systems like cats collapse automatically without measurement. This explains why we never see macroscopic superposition. The theory is testable. Experiments are searching for signatures of objective collapse. So far they have found nothing. The theory also introduces randomness at a fundamental level, making the universe indeterministic even without observers. The relational interpretation claims that quantum states are not absolute but relative to observers. The cat is alive relative to itself and dead relative to itself in different branches, but there is no objective fact about whether the cat is alive. Different observers can disagree about the cat's state, and both are correct from their perspectives. This dissolves the measurement problem by denying that there is a single objective reality. Everything is relational, but this creates new paradoxes about how different observers' perspectives relate to each other. Quantum Bayesianism treats the wave function as a tool for making predictions rather than a description of reality. The wave function represents your knowledge about the system, not the system itself. Collapse is simply updating your beliefs when you gain new information. This interpretation is subjective. Different observers can assign different wave functions to the same system based on their knowledge. The interpretation avoids ontological commitment, but offers no account of what actually exists beyond observers' beliefs. Every interpretation has fatal flaws. Every interpretation requires you to accept something bizarre. Either consciousness causes physical collapse, or infinite parallel universes exist, or faster-than-light influences are real, or randomness is fundamental, or objective reality does not exist, or the wave function is not real. Pick your preferred impossibility. The measurement problem is not about missing data or insufficient technology. It is about the structure of quantum theory itself. The theory gives us two rules that cannot both be true. Either evolution is always unitary and deterministic, or collapse is real and instantaneous. You cannot have both, yet experiments confirm both. Superposition is real, interference patterns prove it, collapse is real, definite measurement outcomes prove it. The theory works perfectly for predictions. It fails completely at explanation. Some physicists argue this is fine. Physics should predict observations, not explain underlying reality. Quantum mechanics does that flawlessly. Asking what really happens during measurement is metaphysics, not science. But this position is intellectually unsatisfying. We are supposed to believe that the most fundamental theory of matter gives no account of what matter is or how it behaves when unobserved. We are supposed to accept that measurement is special without defining what measurement means. Others argue the measurement problem will dissolve once we have a theory of quantum gravity. Perhaps the collapse mechanism involves space-time itself. Perhaps measurement is a gravitational phenomenon. Roger Penrose has proposed that collapse occurs when superpositions create sufficient gravitational instability. The theory is speculative and untested. It requires physics beyond the standard model and beyond general relativity. We have no evidence for it beyond the need to solve the measurement problem. The disturbing possibility remains that consciousness is fundamental. Perhaps collapse requires an observer with subjective experience. Perhaps the universe exists in superposition until a conscious mind interacts with it. This was the view of several founders of quantum mechanics, including Eugene Wigner and John von Neumann. It has been mostly abandoned because it seems to place humans at the center of physics, violating everything we learned from Copernicus onward. But no one has proved consciousness is irrelevant. No one has explained where to draw the boundary between quantum and classical without invoking observation. Experiments keep making the problem worse. Quantum superposition has been demonstrated for larger and larger objects. Molecules containing thousands of atoms, tiny mechanical oscillators, superconducting circuits. Each time, physicists expect to find the boundary where superposition breaks down. Each time, superposition persists. The quantum realm keeps expanding. There is no sign of where it ends. Cats remain hypothetical, but the trajectory is clear. Nothing in the physics prevents macroscopic superposition. Only something outside the physics, something we do not understand, enforces the classical world we experience. The measurement problem is reality's open wound. Quantum mechanics is the most successful theory in science. It explains chemistry, electronics, nuclear physics, particle physics. It has never made a wrong prediction. Yet at its core lies a contradiction we cannot resolve. We use the theory every day without understanding what it means. We build quantum computers and quantum sensors while arguing about whether quantum states are real. The math works, the philosophy is broken, therefore reality is broken, or our description of it is. Somewhere between the quantum and the classical, between the microscopic and the macroscopic, between the objective and the subjective, physics has a hole. The measurement problem is not waiting for a solution, it is waiting for a revolution. But if quantum mechanics threatens the present, the next paradox threatens the past itself. General relativity permits time travel. This is not science fiction. The equations that describe gravity and space-time allow solutions where closed time-like curves exist. A closed time-like curve is a path through space-time that loops back on itself. Follow this path and you return to your own past. You can meet yourself. You can interact with earlier versions of yourself. You can, in principle, prevent your own departure. This is the grandfather paradox, and it reveals that our most trusted theory of gravity allows logical impossibilities. The paradox is simple. Suppose you build a time machine and travel back 50 years. You find your grandfather as a young man before he met your grandmother. You kill him. Your father is never born. You are never born. But if you're never born, you never travel back in time. Your grandfather lives. Your father is born. You are born. You travel back and kill your grandfather. The loop is contradictory. Each outcome prevents itself. Causality collapses into paradox. You might think this proves time travel is impossible. It does not. It proves that if time travel is possible, something must prevent paradoxes. But general relativity does not contain that something. The equations permit closed time-like curves without restriction. They allow you to shoot your grandfather. They allow you to erase your own existence. The math does not care about logical consistency. That is the problem. Kurt Gödel discovered the first closed time-like curve solution in 1949. He found a rotating universe where space-time twists into loops. Travel far enough in one direction, and you return to your own past. Einstein was disturbed. Gödel was his colleague at Princeton. The solution was mathematically rigorous. It satisfied all the equations of general relativity. Einstein had no grounds to reject it except that it seemed absurd. A universe where the past is accessible violates everything we understand about cause and effect. More solutions followed. In 1974, Frank Tipler showed that an infinitely long rotating cylinder creates closed time-like curves in the surrounding space-time. Travel around the cylinder in the right way and you loop back in time. The cylinder must be infinitely long and rotating at nearly the speed of light. Impractical, but not forbidden by physics. The equations allow it. Kip Thorne discovered that wormholes can become time machines. A wormhole is a tunnel through space-time connecting two distant locations. General relativity permits wormholes as solutions to the Einstein field equations. Take a wormhole and move one mouth at high speed relative to the other. Time dilation causes the two mouths to age differently. Now the wormhole connects different times as well as different places. Enter one mouth, and you emerge from the other in the past. You have created a closed time-like curve. Thorne worked out the details with his students in the 1980s. The setup requires exotic matter with negative energy density to hold the wormhole open. We have never observed such matter. But quantum field theory predicts it can exist in small amounts. The physics does not forbid it. Every time physicists find a way to build a time machine within general relativity, they also find that it requires extreme conditions, infinite cylinders, exotic matter, rotating universes. These conditions may not exist in reality, but that is not the point. The point is that the theory allows them. General relativity contains no principle that forbids closed time-like curves. If you can arrange matter and energy in the right configuration, time travel follows automatically. The theory is indifferent to paradox. Stephen Hawking proposed a way out. He called it the chronology protection conjecture. The idea is that unknown laws of physics conspire to prevent closed time-like curves from forming. Whenever you try to build a time machine, something goes wrong. Quantum effects destroy the wormhole. The rotating cylinder tears itself apart. Some mechanism, not yet understood, enforces causality by making time travel impossible in practice, even though the equations allow it in principle. Hawking had no proof. He offered the conjecture as a hope, a belief that the universe must protect itself from paradox even if we do not know how. The conjecture remains unproven. Some calculations suggest that quantum effects near a forming closed time-like curve become infinite, destroying the structure before time travel becomes possible. But these calculations are tentative. They require a theory of quantum gravity, which we do not have. Other calculations suggest that closed time-like curves can form without catastrophic quantum effects. The question is open. Meanwhile, the paradoxes multiply. The grandfather paradox is just the most famous. There are others, equally troubling. The bootstrap paradox involves information or objects that exist without origin. Suppose you travel back in time and give Shakespeare a copy of his complete works, which he then copies and publishes. Where did the plays come from? Not from Shakespeare. He copied them from you, not from you. You got them from history, where Shakespeare wrote them. The information loops through time with no source. It exists without being created. This violates everything we understand about causation. The predestination paradox involves events that cause themselves. You travel back in time to prevent a disaster. Your actions cause the disaster you were trying to prevent. The disaster causes your time travel. The loop is self-consistent but has no external cause. Why did the disaster happen? Because you tried to stop it. Why did you try to stop it? Because it happened. The causal chain is circular. There is no first cause, no initiating event. The loop simply exists. Some physicists argue that self-consistent loops are acceptable. David Deutsch proposed that quantum mechanics resolves time travel paradoxes through branching. When you travel back and shoot your grandfather, the universe splits. In one branch, he dies, and you are never born. In another branch, he survives, and you are born. You come from the second branch but affect the first branch. There is no contradiction because the branches are separate. This solution requires many worlds and allows you to change the past, but only in parallel timelines. Your own past remains unchanged, but this creates new problems. If you can change the past in another timeline, why does causality hold in your own timeline? What prevents someone from another timeline traveling back and changing your past? The many worlds solution trades one set of paradoxes for another set. It preserves logical consistency, but at the cost of multiplying realities and making causation non-local across branches. The Novikov self-consistency principle takes a different approach. Igor Novikov proposed that only self-consistent timelines are possible. If you travel back to shoot your grandfather, something will always prevent you. The gun jams, you miss, you change your mind. The universe conspires to prevent paradoxes by allowing only those events that fit into a consistent history. This sounds like a solution, until you ask how the universe knows what consistency requires. What mechanism enforces self-consistency? The principle describes what must happen, but not how it happens. It replaces paradox with mysterious constraints that have no physical basis. Time travel also threatens free will. If you travel to the past, can you choose your actions? If yes, you can create paradoxes by choosing inconsistently. If no, your actions are predetermined by the requirement of consistency. You become an actor in a fixed script, unable to deviate from events that have already been written. The Novikov principle implies that time travelers have no freedom. They must do what they did, even if they try to do otherwise. This suggests that free will is an illusion even without time travel, since the universe must be arranged to prevent paradoxes even before anyone builds a time machine. Some physicists embrace this conclusion. They argue the universe is a four-dimensional block where past, present, and future all exist simultaneously. Time does not flow. It simply is. From this perspective, time travel is just movement through the block. Paradoxes do not arise because everything that happens has always happened. Your trip to the past was always part of history. But this view eliminates becoming. Nothing changes. Nothing happens. Events do not occur in sequence. They just exist at different time coordinates. This block universe is deterministic and static, incompatible with our experience of time passing and the future being open. Experiments cannot resolve these paradoxes because we cannot build time machines. The engineering requirements are absurd, but the paradoxes are not engineering problems. They are conceptual problems. General relativity, our best theory of space and time, permits situations where cause and effect break down. Either the theory is incomplete, missing some principle that forbids closed time-like curves, or causality is not fundamental. Both options are disturbing. If causality is not fundamental, then the universe does not operate according to cause and effect at the deepest level. Events do not necessarily have causes. The past does not uniquely determine the future. Everything we think we understand about how reality works is wrong. Physics is built on causality. Remove it, and the entire structure collapses. We cannot make predictions. We cannot explain phenomena. Science becomes impossible. If general relativity is incomplete, we need new physics. Quantum gravity might forbid closed time-like curves through mechanisms we have not discovered. But we have no quantum theory of gravity. String theory and loop quantum gravity are candidates, but neither is complete or tested. We are guessing about what might resolve the paradox without evidence to guide us. The problem has persisted for 70 years with no resolution in sight. The grandfather paradox is not about whether you can kill your grandfather. It is about whether the laws of physics permit logical contradictions. General relativity says yes, logic says no. One of them must yield. We do not know which. We do not know how. We only know that time, causality, and consistency are incompatible within our current framework. Reality allows something it should not allow. Physics permits something logic forbids. This is not a puzzle waiting for cleverness. This is a war between mathematics and meaning, and we do not know which side will win. But if the past contains paradoxes, the present contains something even more unsettling. The universe itself should not exist. The universe is calibrated for existence with a precision that defies explanation. Change the strength of gravity by 1 part in 10 to the 34, and stars cannot form. Adjust the electromagnetic force by 4%, and chemistry becomes impossible. Shift the strong nuclear force by 0.5%, and atomic nuclei fall apart. Alter the cosmological constant by 1 part in 10 to the 120, and the universe either collapses immediately or expands so fast that matter never clumps into galaxies. These are not rough estimates. These are measured sensitivities. The fundamental constants of nature sit within absurdly narrow ranges that permit complexity, structure, and life. Step outside those ranges and the universe becomes a sterile void. This is the fine-tuning problem, and it terrifies cosmologists. The constants appear arbitrary. They are not derived from deeper principles. They are simply measured and inserted into equations. The electron has the mass it has. The speed of light has the value it has. These numbers could, as far as we know, be different. Nothing in our theories explains why they take their specific values. Yet those values are precisely what is needed for a universe that contains atoms, stars, planets, and observers. The coincidence is staggering. Start with gravity. The gravitational constant determines how strongly masses attract each other. If gravity were slightly stronger, stars would burn faster and hotter. They would exhaust their fuel in millions of years instead of billions. Life would have no time to evolve. Planets would be crushed by their own weight. If gravity were slightly weaker, stars would never ignite. Gas clouds would drift through space without collapsing. No stars means no heavy elements. No heavy elements means no planets, no chemistry, no life. The window where gravity permits stable stars that last billions of years is incredibly narrow. The electromagnetic force holds atoms together and governs chemistry. Strengthen it and electrons bind too tightly to atomic nuclei. Chemical reactions become impossible. Molecules cannot form. Weaken it and electrons barely stick to nuclei. Atoms fall apart. Chemistry again becomes impossible. The strength of electromagnetism must be balanced precisely against the strength of gravity. If the ratio changes by more than a few percent, either stars cannot form or atoms cannot exist. Both are required. Both depend on the ratio being exactly what it is. The strong nuclear force binds protons and neutrons into atomic nuclei. It must be strong enough to overcome electromagnetic repulsion between protons, but weak enough to allow different nuclei to exist. If the strong force were 5% weaker, deuterium would not be stable. Stars could not fuse hydrogen into helium. The universe would contain only hydrogen, forever. If the strong force was stronger by a similar amount, protons would bind so easily that hydrogen would be rare. Helium would dominate. Stars would burn differently. The elements necessary for life would not form in sufficient quantities. The margin of error is tiny. The weak nuclear force governs radioactive decay and neutrino interactions. It determines how stars burn and how supernovae explode. If the weak force was stronger, the Big Bang would have converted all hydrogen into helium. Stars would have no fuel. If it were weaker, supernovae would not scatter heavy elements into space. Planets would lack carbon, oxygen, nitrogen. These elements are created in stars and disperse by supernovae. Alter the weak force and the cosmic assembly line for heavy elements breaks down. The cosmological constant is the worst. This number represents the energy density of empty space. It drives the accelerating expansion of the universe. Theory predicts it should be enormous, roughly 10 to the 120 times larger than observed. If theory were correct, space itself would tear apart faster than atoms could form. The universe would be empty within fractions of a second. But the observed value is tiny, almost zero but not quite. It is small enough to allow 14 billion years of structure formation, but large enough to eventually dominate and accelerate expansion. Why is it so small? Why is it not exactly zero? No one knows. The discrepancy between prediction and observation is the largest failure in the history of physics, and the observed value sits precisely in the range that allows galaxies to exist. The masses of fundamental particles are equally suspicious. The electron is roughly 2,000 times lighter than the proton. This ratio determines atomic structure. If the electron were heavier, atoms would be smaller and chemistry would change. If it were lighter, atoms would be larger and more fragile. The specific ratio we observe allows for the complexity of organic molecules. Change it and DNA becomes impossible. The proton and neutron have nearly identical masses, differing by less than 1%. If the neutron were slightly lighter, it would not decay outside nuclei. Hydrogen would be unstable. If the proton were lighter than the neutron, all protons would decay into neutrons. Atoms would not exist. The mass difference must be what it is, and no theory explains why. The Higgs field gives particles their masses through interactions. The strength of these interactions determines particle masses. The Higgs field could have any value. The value it has produces the particle masses we observe. A different value would produce a different spectrum of particles, most of which would make structure formation impossible. The Higgs field sits at a value that appears to be balanced on a knife edge. Quantum corrections should drive it to extreme values, either zero or enormous. Instead, it remains stable at a moderate value. This is the hierarchy problem, another fine-tuning puzzle nested inside the larger fine-tuning problem. Some physicists argue fine-tuning is not surprising because we can only observe a universe that permits observers. This is the anthropic principle. Universes that do not allow life contain no one to notice. We necessarily find ourselves in a universe with constants that permit our existence. This reasoning is valid but unsatisfying. It explains why we observe fine-tuning without explaining why fine-tuning exists. It replaces a physical explanation with a selection effect. The anthropic principle gains force if multiple universes exist. If there is a multiverse, a vast ensemble of universes with different constants, then our universe is simply one where the constants happen to allow complexity. Most universes in the ensemble are sterile. We live in a rare one because we must. Fine-tuning is explained by probability across the multiverse, but this explanation requires assuming the multiverse exists. We have no evidence for other universes, we cannot observe them, we cannot test the hypothesis. The multiverse explains fine-tuning by invoking something even more extravagant than fine-tuning itself. String theory predicts a landscape of possible universes, perhaps 10 to the 500 different configurations, each with different constants. If all these configurations are realized somewhere in a multiverse, our universe is just one point in the landscape. But string theory is unproven. The landscape is speculative. We're using one unconfirmed theory to explain a mystery by invoking a structure we cannot observe. This is not science. This is metaphysics dressed in equations. Some propose that constants are not fixed but evolve. Lee Smolin suggested that universes reproduce through black holes. Each black hole spawns a new universe with slightly different constants. Universes with constants that produce many black holes have more offspring. Over countless generations, the ensemble evolves toward constants that maximize black hole production. It happens that such constants also permit stars, heavy elements, and potentially life. This cosmological natural selection is clever but untestable. We cannot observe other universes or their reproduction. The hypothesis explains fine-tuning but cannot be verified. Others suggest constants are determined by deeper principles we have not discovered. Perhaps a unified theory will reveal that the constants must have the values they have. This would eliminate fine-tuning by showing the constants are not arbitrary. But decades of effort to unify physics have not produced such a theory. The standard model has 19 free parameters that must be measured experimentally. A true unified theory should derive these parameters from fundamental principles. No candidate theory has succeeded. The constants remain unexplained. The alternative is design. If the universe is calibrated for life, perhaps something calibrated it. This argument is old and has been rejected by science for centuries, but fine-tuning gives it renewed force. The precision required is so extreme that chance seems inadequate, and physical necessity seems absent. Design offers an explanation, but it is not a scientific explanation. It does not make predictions. It does not suggest experiments. It terminates inquiry by invoking an external agent. Science cannot work with design as an answer. The fine-tuning problem is not about individual constants. It is about their relationships. The constants must be coordinated. Gravity must be weak compared to electromagnetism by exactly the right amount. The strong force must be balanced against electromagnetism. The cosmological constant must be small enough not to dominate early, but large enough to dominate late. These relationships suggest the constants are not independent but connected by some underlying structure. Yet we see no structure. We have no equations that relate the constants to each other. They appear independent and arbitrary, yet they conspire to permit existence. Some constants are dimensionless, pure numbers independent of measurement units. The fine structure constant, roughly 1 divided by 137, governs electromagnetic interactions. It is a pure number with no units. Why does it have this value? No theory explains it. Richard Feynman called it one of the greatest mysteries in physics. The ratio of electron mass to proton mass is another dimensionless constant. These pure numbers are especially mysterious because they cannot be explained by choice of units. They are fundamental features of reality. The fine-tuning extends beyond particle physics. The universe's initial conditions were also fine-tuned. The density of matter at the Big Bang was almost exactly the critical density needed to balance expansion against gravitational collapse. Deviate by 1 part in 10 to the 60, no structure forms. The early universe was also incredibly smooth, with density variations of only 1 part in 100,000. Too smooth and no structure forms. Too rough and black holes dominate. The initial conditions sit precisely in the range that allows galaxies and stars to form over billions of years. The entropy of the early universe was extremely low. Low entropy is an improbable state. The universe began in a configuration that was extraordinarily special, one of the rarest possible arrangements. Why? High entropy is vastly more probable. The universe should have started in thermal equilibrium, a maximum entropy state where nothing interesting happens. Instead, it started far from equilibrium, creating the arrow of time and allowing complex structures to emerge. This initial low entropy is another form of fine-tuning, one that operates at the level of the universe's entire state rather than individual constants. Every proposed explanation for fine-tuning has fatal problems. The anthropic principle requires a multiverse we cannot observe. Cosmological natural selection requires universe reproduction we cannot test. Deeper principles require theories we do not have. Design requires abandoning naturalistic explanation. Chance requires accepting that we won a cosmic lottery with odds of 1 in 10 to the 120 or worse. None of these options are satisfying. All require believing in something beyond evidence. The fine-tuning problem suggests our physics is incomplete. A complete theory should explain why the constants have their values. It should derive them from deeper principles, or show that they are the only values compatible with mathematical consistency. Our current theories do neither. They treat constants as inputs rather than outputs. This is a sign of incompleteness, a placeholder for understanding we do not yet have. Fine-tuning is the universe telling us we're missing something fundamental, but perhaps the constants are not the deepest mystery. Perhaps the deeper question is why there is something rather than nothing. Why does a universe exist at all? Why are there laws of physics? Why is there mathematics? These questions lie beyond current physics. They may lie beyond science entirely. But fine-tuning forces us to confront them because the constants are so precisely arranged that the universe appears intentional. It appears designed for observers. Whether that appearance is illusion or insight, we cannot yet say. The next paradox suggests we may not be alone in this finely tuned cosmos. But if we are not alone, where is everyone? The Milky Way contains between 100 billion and 400 billion stars. Most of those stars have planets. Estimates suggest at least 100 billion planets exist in our galaxy alone. Many orbit in habitable zones where liquid water can exist. The galaxy is 13 billion years old. Earth is 4.5 billion years old. Life appeared on Earth within a few 100 million years of the planet becoming habitable. Intelligence emerged after 4 billion years. If this timeline is typical, countless civilizations should have arisen long before humanity. Some should be millions or billions of years more advanced. They should be everywhere. They should be obvious. We should see their megastructures, detect their signals, observe their engineering projects reshaping solar systems. We see nothing. We hear nothing. The universe is silent. This is the Fermi paradox, and it suggests something is deeply wrong with our assumptions about life, intelligence, or survival. Enrico Fermi asked the question in 1950 during a casual lunch conversation: if intelligent life is common, where is everybody? The question sounds simple. The implications are devastating. The numbers support life being common. The Drake equation formalizes the calculation. Start with the rate of star formation. Multiply by the fraction of stars with planets. Multiply by the number of planets in habitable zones per star. Multiply by the fraction where life actually develops. Multiply by the fraction where intelligence evolves. Multiply by the fraction that develops technology detectable across interstellar space. Multiply by the length of time such civilizations remain detectable. Even conservative estimates produce thousands of detectable civilizations in our galaxy right now. Optimistic estimates produce millions. We have searched. The search for extraterrestrial intelligence has monitored radio frequencies for decades. Hundreds of thousands of stars have been surveyed. Billions of radio channels scanned. The searchers have found nothing. No signals, no patterns, no indication of artificial transmission. The WOW signal detected in 1977 looked promising for a few hours. It has never repeated. Every other candidate signal has been traced to terrestrial interference or natural astrophysical sources. The silence is complete. Optical searches look for laser pulses. Infrared searches look for waste heat from advanced civilizations. Studies examine stars for signs of megastructures like Dyson spheres that would block starlight in characteristic patterns. Tabby's star showed unusual dimming that briefly excited researchers. Natural explanations involving dust clouds now seem more likely. Every search has returned negative results. If advanced civilizations exist, they are not doing anything we can detect. They are not broadcasting. They are not building on visible scales. They are hiding, or they are gone, or they never existed. The paradox deepens when you consider travel time. Even without faster-than-light travel, a civilization could colonize the galaxy in a few million years using slower-than-light spacecraft. Send probes to nearby stars. Those probes build copies of themselves. The copies spread to more stars. Exponential expansion fills the galaxy quickly on cosmic timescales. The Milky Way is billions of years old. Even one expansionist civilization anywhere in the galaxy's history should have reached everywhere by now, including Earth. We should see evidence of colonization, ancient artifacts in our solar system, probes in orbit, ruins on the moon. We find nothing. Perhaps intelligent life is rare. Perhaps one or more steps in the chain from star formation to detectable civilization have extremely low probability. This is the rare Earth hypothesis. Maybe life itself is rare. Maybe the transition from simple to complex life is rare. Maybe intelligence is rare. Maybe technological civilization is rare. If any of these steps has a probability low enough, it could explain why we see no one. But this requires accepting that we are extraordinarily lucky or extraordinarily special. Earth would be one of the only planets in the galaxy, perhaps in the observable universe, to produce technological intelligence. The Copernican principle, which says we are not special, would be violated spectacularly. Perhaps intelligence is common, but technological civilization is not. Many species are intelligent without developing technology. Dolphins, elephants, octopuses show complex cognition, but do not build radios. Maybe the path from intelligence to technology requires specific conditions that rarely occur. Opposable thumbs, fire, social structures that permit knowledge accumulation. If these conditions are rare, most intelligent species never develop the capability to signal across space. But this still requires explaining why no one else in the galaxy achieved what we achieved. Perhaps civilizations destroy themselves. This is the self-destruction hypothesis. Once a species develops nuclear weapons, artificial intelligence, biotechnology, or nanotechnology, it faces existential risks. Nuclear war could sterilize a planet. Runaway AI could eliminate its creators. Engineered pathogens could cause extinction. Climate collapse could make planets uninhabitable. If most civilizations destroy themselves shortly after becoming detectable, the galaxy could be full of ruins and silent graveyards. The window where a civilization is both technological and surviving is brief. We may be in that window now, soon to exit. The Great Filter is a generalization of this idea. Somewhere between lifeless planets and galaxy-spanning civilizations, there is a filter, a step so difficult that almost no one passes through. Either the filter is behind us, meaning the hard steps are in our past and we are extraordinarily rare, or the filter is ahead of us, meaning civilizations like ours typically do not survive much longer. If the filter is ahead, our future is bleak. We're approaching the stage where most civilizations fail. The silence of the galaxy is a warning. Perhaps advanced civilizations are quiet intentionally. The zoo hypothesis suggests they know we are here and choose not to contact us. Maybe there is a galactic protocol to avoid interfering with developing civilizations. We are being observed but not contacted, like animals in a zoo. This preserves our natural development without contamination from outside. The hypothesis is unfalsifiable. If they are hiding perfectly, we cannot detect them. If we cannot detect them, we cannot prove they exist. The hypothesis explains the silence but cannot be tested. The dark forest hypothesis is more sinister. Maybe the galaxy is full of civilizations, but they stay silent because broadcasting is dangerous. Any civilization that reveals itself becomes a target. Advanced civilizations eliminate emerging ones preemptively to remove future threats. The galaxy is a dark forest where every civilization is a hunter, moving quietly, listening for others, ready to destroy anything that makes noise. We are children shouting in the forest, unaware of the predators. If this is true, our radio transmissions for the past century may have been catastrophic mistakes. We may have already been noticed. The silence is not absence, it is predation. Perhaps we are first. The firstborn hypothesis suggests intelligence had to emerge somewhere eventually. Maybe we are among the earliest civilizations in the galaxy. The universe is only 14 billion years old. The first stars contained no heavy elements. Planets could not form until stars created carbon, oxygen, silicon through fusion, and scattered them in supernovae. This took billions of years. Perhaps Earth formed at the earliest possible time when conditions permitted complex life. If so, we are not late, we are early. The galaxy will fill with civilizations eventually, but we are among the first. This is statistically unlikely but not impossible. Perhaps intelligence is common but communication is not. Civilizations might exist without using radio. They might communicate through channels we have not imagined. Neutrinos, gravitational waves, quantum entanglement. If advanced civilizations use technologies we do not understand, we would not recognize their signals. We are listening on the wrong frequencies, looking for the wrong signatures. They are all around us, communicating constantly, and we are deaf and blind to it. Perhaps post-biological civilizations have no interest in expansion. Once a civilization develops artificial intelligence or uploads consciousness into machines, it might turn inward. Virtual realities could be more appealing than physical space. Why colonize planets when you can create infinite digital worlds? Advanced civilizations might exist as computronium, matter optimized for computation, processing unimaginable simulations. They would be invisible to us. We would see stars that seem normal but contain entire civilizations running on substrate. We cannot distinguish from natural matter. Perhaps faster than light travel is impossible, and interstellar distances are simply too large. Even at a significant fraction of light speed, traveling between stars takes decades or centuries. Colonizing the galaxy takes millions of years. Maybe civilizations are out there, but they are isolated by distance. They cannot reach us. We cannot reach them. The speed of a light enforces isolation. The galaxy is populated but fragmented. No one can communicate with anyone else on timescales shorter than centuries. Civilizations rise and fall before messages arrive. The galaxy is full of life that will never meet. Perhaps we are living in a simulation. If advanced civilizations run ancestor simulations, detailed reconstructions of their evolutionary past, then most conscious observers exist in simulations rather than base reality. You are more likely to be a simulated observer than a real one. If we are in a simulation, the Fermi paradox is explained. The simulation contains only Earth because the simulators are interested only in us. There are no aliens because the simulation is not designed to include them. This hypothesis is metaphysically disturbing and empirically empty. It explains everything and predicts nothing. Every proposed solution to the Fermi paradox has weaknesses. The rare Earth hypothesis requires accepting we are special. The self-destruction hypothesis requires believing survival is nearly impossible. The zoo hypothesis requires coordinated galactic silence. The dark forest requires universal paranoia. The firstborn hypothesis requires accepting improbable timing. The technological mismatch hypothesis requires assuming we are fundamentally limited. Each solution trades one mystery for another. None are satisfying. The paradox suggests one of our assumptions is badly wrong. Either life is far rarer than we think, or intelligence is far rarer, or technological civilizations are far rarer, or they do not last, or they do not expand, or they do not communicate, or we are alone. Every option is disturbing. If we are alone, the universe is unimaginably empty. If we're not alone, something prevents contact, and that something could be our own imminent extinction. The search continues. New telescopes scan more stars. New methods search for biosignatures in exoplanet atmospheres. New strategies look for technosignatures like industrial pollution or artificial lighting on distant worlds. So far, nothing. The silence persists, and the longer it persists, the more ominous it becomes. The Fermi paradox is not just about where aliens are. It is about what happens to civilizations like ours. The galaxy may be full of answers, or it may be full of graves. We do not know which. We only know that we are shouting into darkness, and the darkness does not answer. But perhaps the silence is not the strangest thing about the cosmos. Perhaps the strangest thing is something we see every night. Look up at the night sky. It is dark. This seems obvious, trivial, not worth mentioning. But the darkness is impossible. If the universe is infinite and filled with stars, every line of sight from Earth should eventually intersect a star's surface. The entire sky should blaze with the combined light of infinite stars. The night should be as bright as day, brighter. The sky should be a solid wall of starlight. It is not. This is Olbers's paradox, named after the German astronomer Heinrich Wilhelm Olbers, who discussed it in 1826, though others noted the problem centuries earlier. The paradox reveals that something fundamental about the universe contradicts our intuitive assumptions. The reasoning is straightforward. Imagine the universe extends infinitely in all directions. Stars are distributed roughly uniformly throughout this infinite space. Pick any direction and look. Your line of sight travels outward. Eventually, perhaps after billions of light years, it reaches a star. That star contributes light to what you see. Now consider all possible directions. Every direction eventually hits a star if space is infinite and stars are everywhere. Therefore, every point in the sky should glow with starlight. The fact that distant stars are fainter does not save the argument. Yes, a star twice as far away appears 4 times dimmer. But in a shell of space twice as far away, there are 4 times as many stars. The increased number exactly compensates for the decreased brightness. The total light from each shell is the same regardless of distance. Add up infinite shells and you get infinite brightness. The sky should be blindingly bright. It is not. The night sky is dark except for a few thousand visible stars and the faint band of the Milky Way. Most of the sky is black. This darkness needs explanation. Something must be wrong with the assumptions. Either the universe is not infinite, or stars are not distributed uniformly, or something else intervenes to prevent infinite brightness. One proposed solution is that dust absorbs starlight. Clouds of gas and dust between stars block light from distant sources. This seems plausible until you calculate the consequences. If dust absorbs infinite starlight, the dust heats up. It radiates that energy as infrared light. The sky would still be bright, just in infrared rather than visible light. The paradox is not solved. It is merely shifted to a different wavelength. Observations show the infrared sky is not uniformly bright either. Dust does not resolve the paradox. Another solution is that the universe is not infinite. If space is finite, containing only a finite number of stars, then most lines of sight do not intersect stars. They reach the edge of the star-filled region and continue into empty darkness. This avoids infinite brightness, but requires accepting that the universe has an edge or a finite volume. Modern cosmology suggests the universe is either infinite or so large that its curvature makes it effectively finite but unbounded, like the surface of a sphere. If the universe is finite, the paradox is solved, but observations suggest the universe is flat and possibly infinite. The solution is uncertain. The correct resolution involves time and expansion. The universe is not infinitely old. It began 14 billion years ago at the Big Bang. Light travels at a finite speed. Therefore, we can only see stars whose light has had time to reach us. The observable universe has a horizon, a maximum distance from which light has had time to arrive. Beyond that horizon, stars exist, but their light has not reached us yet, because they extend beyond the observable horizon into regions we cannot see. The night sky is dark because the universe is young and light has not had time to fill it. This solution works but requires the Big Bang. An eternal static universe would still produce Olbers's paradox. The darkness of the night sky is evidence that the universe has a finite age. Every time you see a dark sky, you are seeing proof that the cosmos began. The darkness is fossil evidence of the Big Bang, visible to anyone who looks up. Expansion adds another layer. The universe is not static. Space itself is expanding, carrying distant galaxies away from us. Light from those galaxies is redshifted, stretched to longer wavelengths by the expansion. Visible light becomes infrared. Infrared becomes microwave. Eventually, light is redshifted so much that it becomes undetectable. This redshift dims distant sources more than their distance alone would predict. Expansion darkens the sky further, ensuring that even if the universe is infinite, the combined light from all sources remains finite. The most distant visible galaxies are faint not just because they are far, but because their light has been stretched and diluted by billions of years of expansion. The cosmic microwave background is the ultimate consequence of this redshift. The universe was once hot and dense, filled with glowing plasma. That primordial light has been travelling through space for 14 billion years, redshifted by expansion from visible light to microwaves. The cosmic microwave background is the glow of the early universe, stretched and cooled into invisibility to the naked eye. It is there, filling the sky uniformly, but we need microwave detectors to see it. In a sense, the sky is bright. It is just bright in wavelengths we cannot see without instruments. The visible darkness hides a microwave glow. Olber's paradox is resolved by cosmology. The universe is finite in age and expanding. These two facts prevent infinite brightness. But the paradox served a crucial role historically. It demonstrated that the universe cannot be both infinite, eternal, and static. At least one of those assumptions must be wrong. Before the Big Bang theory, astronomers assumed the universe was eternal and unchanging. Olber's paradox proved that assumption was incompatible with the dark night sky. The darkness demanded either a beginning or expansion or both. Cosmology eventually confirmed both. The paradox also illustrates how everyday observations can reveal deep truths. You do not need a telescope or a particle accelerator to see evidence of the Big Bang. You just need to notice that the sky is dark at night and ask why. The answer leads directly to the most important discovery in cosmology. The universe is not eternal. It had a beginning. It is evolving. The darkness is not absence. It is information, telling us that time has a starting point and space is changing. But darkness is not the only mystery the sky presents. The uniformity of the cosmic microwave background hides another paradox, one that challenges causality itself. The cosmic microwave background is the same temperature in every direction, to within 1 part in 100,000. Measure the temperature of the microwave glow from one side of the sky. Measure it from the opposite side. The values match almost perfectly. This uniformity is remarkable because those two regions of space have never been in contact. Light from one region has not had time to reach the other since the Big Bang. They are beyond each other's horizons, yet they have the same temperature. This is the horizon problem, and it suggests that the early universe was coordinated in ways that should not be possible. Temperature uniformity requires equilibrium. If two regions have the same temperature, energy has flowed between them until they equalize. Heat flows from hot to cold until everything reaches the same temperature. This is basic thermodynamics, but heat transfer requires communication. Information must travel from one region to the other, carried by particles or radiation. That transfer cannot happen faster than light. If two regions are too far apart for light to have traveled between them, they cannot equalize. They should have different temperatures, reflecting whatever random conditions existed when they formed. The cosmic microwave background comes from a time when the universe was 380,000 years old. At that time, space had expanded enough that regions on opposite sides of the observable universe were already separated by distances larger than light could have crossed since the Big Bang. These regions were causally disconnected. No signal could have passed between them, yet they had the same temperature to extraordinary precision. How did they know to be the same? What coordinated them? You can calculate the size of causally connected regions at that time. Light travels at a finite speed. In 380,000 years, light travels 380,000 light years. Any region larger than this should show temperature variations, because different parts could not have communicated. But the cosmic microwave background comes from regions millions of light years across, all at the same temperature. The uniformity extends far beyond the causal horizon. It is as if someone reached across unbridgeable distances and synchronized the temperature everywhere. This is not a small discrepancy. The observable universe today is 93 billion light-years across. At the time of the cosmic microwave background, it was much smaller, but still divided into thousands of causally disconnected regions. Each region should have evolved independently with its own temperature determined by local conditions. Instead, all regions have the same temperature. The probability of this happening by chance is astronomically small. It is like flipping a coin 1,000 times and getting heads every time. Possible, but so unlikely that it demands explanation. The standard Big Bang model has no explanation. It simply accepts the uniformity as an initial condition. The universe started smooth. Why? No reason. It just did. This is deeply unsatisfying. Physics should explain why things are the way they are, not accept them as brute facts. The horizon problem reveals that the standard Big Bang model is incomplete. Something must have made the early universe uniform before the cosmic microwave background formed. Inflation is the proposed solution. In the first fraction of a second after the Big Bang, the universe underwent exponential expansion. Space expanded faster than light, doubling in size every tiny fraction of a second. This inflation lasted perhaps 10 to the negative 30 seconds. During that time, the universe grew by a factor of at least 10 to the 26. A region smaller than an atom expanded to larger than the observable universe today. This solves the horizon problem by making the observable universe come from a single tiny causally connected region. Before inflation, the entire observable universe was small enough that light could cross it. Temperature equalized. Then, inflation blew that small uniform region up to enormous size. The cosmic microwave background is uniform because it all came from the same tiny patch that had time to equilibrate before inflation began. Inflation works as a solution. It explains not just the horizon problem but several other features of the universe. It explains why space is flat. It explains the origin of density fluctuations that seeded galaxies. It makes testable predictions that have been confirmed. Inflation is the leading theory of the early universe, but it is not without problems. Inflation requires a new field, the inflaton field, that drove the exponential expansion. This field has never been observed. We do not know what it is or why it exists. We do not know what started inflation or what stopped it. The theory has many free parameters that must be tuned to match observations. Different versions of inflation make different predictions, and there are hundreds of versions. Inflation is less a single theory than a broad framework with many possible implementations. Some critics argue it is too flexible, capable of explaining almost any observation, which makes it unfalsifiable. Inflation also has a fine-tuning problem of its own. The inflaton field must start with the right energy density and the right initial conditions to produce the universe we observe. If the initial conditions are slightly wrong, inflation either does not start or it never stops, or it produces a universe completely unlike ours. The range of initial conditions that work is narrow. This means inflation may solve the horizon problem by replacing one fine-tuning puzzle with another. Why did the inflaton field have the right initial conditions? We have no answer. Some versions of inflation produce eternal inflation. Once inflation starts in some region, quantum fluctuations cause it to continue forever in most places. Inflation stops in some pockets, creating bubble universes like ours. But overall, inflation never ends. It continues producing infinite bubble universes with different properties. This multiverse scenario explains fine-tuning through selection. but it makes the theory untestable. We cannot observe other bubbles. We cannot verify that eternal inflation happens. The theory predicts things we can never check. Paul Steinhardt, one of the original developers of inflation, has become a critic. He argues that inflation has been modified so many times to fit new observations that it has lost predictive power. Any observation can be accommodated by adjusting parameters or choosing a different version of inflation. A theory that can explain anything explains nothing. Steinhardt and others have proposed alternatives like cyclic cosmology, where the universe undergoes repeated cycles of expansion and contraction. These alternatives have their own problems and are less developed than inflation, but they highlight that inflation is not the only game in town. The horizon problem exposes a fundamental tension in cosmology. We need the early universe to be smooth to explain what we observe, but smoothness requires coordination across regions that could not communicate. Inflation provides a mechanism, but at the cost of introducing unobserved fields and untestable multiverse scenarios. Either we accept inflation with its baggage, or we accept that the universe began in an incredibly special state for reasons we do not understand. Neither option is satisfying. Both suggest our understanding of the very early universe is incomplete. The uniformity of the cosmic microwave background is one of the most precisely measured facts in cosmology. It is also one of the most puzzling. Every time we improve measurements, the uniformity becomes more exact, and the horizon problem becomes sharper. The universe is telling us something. It is telling us that causality as we understand it does not apply to the earliest moments. Either information travelled faster than light, or the universe was born uniform, or something beyond our current physics operated at the beginning. The smooth sky is hiding a profound mystery about how the cosmos began. But if space and time are strange at cosmic scales, they are stranger still when objects move at high speeds. You and your twin board separate spaceships. Your twin accelerates to 90% the speed of light, travels to a distant star and returns. When you reunite, your twin is younger. Years have passed for you. Months have passed for your twin. This is not science fiction. This is special relativity verified by countless experiments. Time genuinely passes at different rates for observers in relative motion. The paradox is that the situation appears symmetric. From your twin's perspective, you are the one who moved away and returned. Your twin should see you as younger, yet only one of you actually ages less. Both perspectives cannot be correct, but both seem equally valid. This is the twin paradox, and it reveals that time is not what we think it is. Special relativity states that time dilation is real. A moving clock runs slower than a stationary clock. The faster you move, the more time slows. At 90% light speed, time passes at about 43% the normal rate. Travel for 1 year at that speed and nearly 2.5 years pass for stationary observers. This is not an illusion caused by light travel time. It is not a mechanical effect on clocks. It is time itself dilating. Every physical process slows. Heartbeats, radioactive decay, atomic vibrations, everything. The effect has been measured. Atomic clocks flown on airplanes show less elapsed time than identical clocks left on the ground. Muons created in the upper atmosphere by cosmic rays should decay long before reaching the ground based on their known half-life. But they survive because time dilation extends their lifespan from their own reference frame. GPS satellites must correct for time dilation, or they would accumulate positioning errors of kilometers per day. Time dilation is not theoretical speculation. It is engineering fact. The twin paradox arises from applying time dilation symmetrically. If your twin moves away from you at high speed, you observe your twin's clock running slow, but moving. Special relativity says all inertial motion is relative. There is no absolute rest frame, so your twin should see your clock running slow. When you reunite, each of you should find the other has aged less. This is contradictory. Only one outcome is possible. Who is actually younger? The resolution involves acceleration. The situation is not symmetric because your twin accelerates. Your twin starts at rest relative to you, accelerates to high speed, coasts, decelerates at the distant star, accelerates back toward you, and decelerates to stop. You remain in an inertial reference frame the entire time. Your twin does not. Your twin changes reference frames multiple times. Special relativity applies to inertial frames, frames moving at constant velocity. Acceleration breaks the symmetry. The twin who accelerates is the one who ages less. This answer is correct but unsatisfying because it does not explain how acceleration causes the asymmetry. What is special about acceleration? During the coasting phase, when your twin is moving at constant velocity, both of you see the other's clock running slow. This seems paradoxical, even if acceleration breaks the symmetry later. The resolution requires understanding relativity of simultaneity. Simultaneity is relative. Events that are simultaneous in one reference frame are not simultaneous in another frame moving relative to the first. This is not about signal delays, it is about the actual ordering of events in time. When your twin accelerates, the reference frame changes. What counts as now for your twin shifts dramatically. During the outbound trip, your twins now corresponds to an earlier time for you. During the return trip, your twins now corresponds to a much later time for you. The acceleration causes a sudden jump in what your twin considers simultaneous with your current age. This jump accounts for the missing time. Your twin sees your clock running slow during the outbound trip, then suddenly jump forward during the turnaround, then run slow again during the return trip. The jump more than compensates for the slow periods. When you reunite, you have aged more. From your perspective, the explanation is simpler. You remain in a single inertial frame. You see your twin's clock running slow the entire trip. When your twin returns, your twin has genuinely aged less. No jumps, no complications. The asymmetry is clear because you never accelerated. The paradox is not a true contradiction. It is a confusion arising from incorrectly applying special relativity. Once you account for acceleration and relativity of simultaneity, the paradox dissolves. But the resolution is conceptually disturbing. Time is not a universal background against which events occur. Time is observer-dependent. Different observers slice space-time into space and time in different ways. What is simultaneous for one observer is not simultaneous for another. The present is not an objective moment shared by everyone. It is a subjective surface that changes depending on your motion. This relativity of time undermines common sense. We experience time as flowing uniformly for everyone. We imagine that somewhere far away, events are happening right now, simultaneously with what happens here. Special relativity says this is wrong. There is no universal now. The present is a local concept defined relative to your reference frame. Distant events that you consider simultaneous with this moment are different depending on how you are moving. Change your velocity and you change what you consider now. The twin paradox can be made more extreme. Send your twin on a longer trip at higher speed. At 99.9% light speed, time dilation is about 22:1. Your twin travels for 1 year subjective time. 22 years pass for you. At 99.99% light speed, the ratio becomes 70:1. Your twin could travel for a year and return to find you 70 years older. Push closer to light speed and the ratio grows without limit. Your twin could travel for a few months and return thousands of years in the future. This is time travel into the future. It is permitted by special relativity. Achieving the necessary speeds is an engineering challenge, but the physics allows it. Travel near light speed and you move into the future relative to everyone else. You age slowly. The universe ages normally. When you stop, you find yourself in the distant future. This is not speculation. This is how relativity works. Time dilation makes forward time travel possible, at least in principle, but the asymmetry remains. You can travel into the future. You cannot travel into the past. The twin paradox does not allow backward time travel. Acceleration always moves you forward in time relative to inertial observers, never backward. Special relativity forbids closed time-like curves. General relativity allows them in specific exotic spacetimes, creating the paradoxes discussed earlier. But special relativity, which applies to flat spacetime without gravity, keeps causality intact. You can age less than others, but you cannot arrive before you left. The twin paradox also applies to general relativity. Gravity causes time dilation. Clocks in strong gravitational fields run slower than clocks in weak fields. This is gravitational time dilation, distinct from the kinematic time dilation caused by motion. An observer near a black hole's event horizon experiences extreme time dilation. 1 hour near the horizon could correspond to years far from the black hole. This is depicted in the film Interstellar. The scenario is scientifically accurate. Gravitational time dilation is real and measurable. Combine kinematic and gravitational time dilation, and you get complex scenarios. A twin who travels at high speed through regions of varying gravitational potential will experience time differently than a twin who remains stationary in a different gravitational field. Calculating who ages more requires integrating both effects along each twin's world line through spacetime. The mathematics is straightforward, but the conceptual picture is bizarre. Time is not universal. It is local, variable, dependent on motion and gravity. The twin paradox forces us to confront the relativity of time. Time is not absolute. It does not flow at the same rate everywhere. It is affected by motion and gravity in measurable ways. This is verified by experiment. GPS satellites, particle accelerators, atomic clocks all confirm it. Yet our intuition rebels. We feel that time is universal, that now is the same for everyone. Special relativity proves this feeling is wrong. Time is relative. Different observers experience different amounts of time between the same events. There is no preferred reference frame, no absolute clock ticking away the true time. This relativity extends to space. Distances are not absolute either. A moving object is length contracted along its direction of motion. A spaceship travelling at 90% light speed is contracted to about 43% of its rest length as measured by a stationary observer. From the spaceship's perspective, it is stationary and the universe is contracted. The distance to the destination is shorter in the ship's frame than in the rest frame of the destination. Both perspectives are valid. Space, like time, is observer-dependent. Special relativity unifies space and time into space-time, a four-dimensional structure where the separation between events depends on the observer. What one observer considers a separation in space, another observer considers partly a separation in time. Space and time are not independent. They are interwoven aspects of a single entity. The twin paradox demonstrates this. The twins disagree about how much time elapsed and about what events are simultaneous. They are slicing space-time differently, each valid within their own frame. The paradox is resolved mathematically, but the resolution does not eliminate the strangeness. Time genuinely behaves in ways that violate everyday intuition. Twins can age at different rates. The present is not universal. Time travel into the future is possible. These are not philosophical puzzles. These are physical facts about the universe. The twin paradox is not a paradox in the sense of a logical contradiction. It is a paradox in the sense of a truth that seems impossible but is not. The implications are unsettling. If time is relative, what is time? If simultaneity is observer-dependent, what does it mean for events to happen now? If you can travel into the future by moving fast, does the future already exist? Special relativity does not answer these questions. It describes how time behaves without explaining what time is. The equations work, the predictions are confirmed, but the ontology remains mysterious. Time is a dimension of space-time, but what does that mean? Is the future real? Is the past still real? Does anything flow? Or is time a static dimension we move through? These questions connect to the block universe interpretation of relativity. If all of space-time exists as a four-dimensional structure, then past, present, and future are equally real. Nothing flows, nothing becomes. Events simply exist at different time coordinates. From this view, the twin paradox is straightforward. Each twin follows a different path through space-time. The paths have different lengths when measured in proper time. There is no paradox, just different path lengths. But the block universe eliminates becoming. Nothing happens, events do not occur, they just are. This contradicts our deepest experience of time passing, of the future being open and the past being fixed. The twin paradox forces us to choose between our intuition and the mathematics. The mathematics is clear, intuition must yield. But yielding intuition comes at a cost. We must accept that time is not what it seems. We must accept that reality is stranger than experience suggests. Yet even special relativity's strangeness pales compared to what quantum mechanics reveals about reality. Albert Einstein never accepted quantum mechanics. He spent the last decades of his life fighting it, searching for flaws, devising thought experiments to expose contradictions. In 1935, he published a paper with Boris Podolsky and Nathan Rosen, presenting what he considered the death blow to quantum theory. The EPR paradox, named for its authors, described a scenario where quantum mechanics made predictions that Einstein believed were impossible. Two particles interact and become entangled. They separate. You measure one particle. Instantly, the other particle's state becomes determined, no matter how far away it is. Measure the first particle's spin as up, and the second particle's spin becomes down, instantaneously, across any distance, even if the particles are on opposite sides of the galaxy. Einstein called this spooky action at a distance. He rejected it. Nothing can travel faster than light. No signal can cross space instantaneously. Yet quantum mechanics predicted exactly that. Measure one particle, and you instantly affect the other. The correlation is perfect. It cannot be explained by the particles carrying predetermined values, because quantum mechanics says they do not have definite values until measured. The particles exist in superposition. Both spins are undefined. Measurement collapses the superposition for both particles simultaneously. This violates locality, the principle that objects are only influenced by their immediate surroundings. Distant events should not have instantaneous effects. Einstein proposed an alternative. Maybe the particles do carry hidden information that determines their measurement outcomes. Maybe quantum mechanics is incomplete, missing variables that specify the particles' states precisely. The particles are not truly in superposition. They have definite properties all along. We just do not know what those properties are until we measure. This hidden variable theory would restore locality. The particles do not communicate. They simply reveal information they carried from the beginning. The correlations are not spooky. They are predetermined. For 30 years, the EPR paradox remained a philosophical debate. Quantum mechanics made its predictions. Hidden variable theories made theirs. Both seemed to match experiments. Then, in 1964, John Stuart Bell proved that hidden variables and quantum mechanics make different predictions. Bell derived an inequality that must be satisfied if hidden variables exist and locality holds. If quantum mechanics is correct, the inequality is violated. The predictions are different. The debate became testable. Experiments began in the 1970s. Alana Speck performed the definitive test in the 1980s. The results were unambiguous. Bell's inequality is violated. Quantum mechanics is correct. Hidden variables are ruled out, at least the local kind. The correlations between entangled particles are stronger than any local hidden variable theory can explain. Nature is non-local. Measuring one particle genuinely affects the other instantaneously, regardless of separation. This is not theory. This is experimental fact. Entangled photons have been separated by hundreds of kilometers. Measurements on one photon show instant correlations with the other photon's behavior. The speed of the correlation has been tested. If some signal travels between the particles, it must move at least 10,000 times the speed of light. More likely, the correlation is truly instantaneous. Space does not separate entangled particles. They remain connected in a way that transcends distance. The implications are staggering. Reality is non-local. Events here can instantly affect events there without anything traveling through the space between. This seems to violate special relativity, which forbids faster than light signaling. But entanglement does not allow faster than light communication. You cannot use it to send messages. The measurement outcomes are random. You cannot control what result you get. The correlations only appear when you compare results from both sides. Until you bring the data together through normal slower than light communication, you do not see the correlation. So causality is preserved. You cannot use entanglement to send information backward in time or violate causality. But you also cannot explain the correlations through any local mechanism. Quantum mechanics says the particles do not have definite states until measured. Before measurement, they exist in a superposition. The wave function describes both particles together as a single entangled system. Measure one particle, and the wave function collapses. The collapse is instantaneous and affects both particles. This is standard quantum mechanics. It makes correct predictions, but it requires accepting that measurement has non-local effects. Collapse is instantaneous across space. The alternative is to deny that collapse happens. The many worlds interpretation says causes the universe to split. When you measure the first particle and see spin up, the universe branches. In one branch, you saw spin up and the other particle is spin down. In another branch, you saw spin down and the other particle is spin up. Both outcomes occur in different branches. The correlation is explained because the branches are correlated. You and the distant particle are entangled with each other. The non-locality is not between particles. It is between branches of the wave function. This preserves locality in a sense, but at the cost of infinite parallel universes. Pilot wave theory also avoids instantaneous collapse by making the wave function real and guiding particles with definite positions. The wave function is non-local. It extends across space and responds instantly to measurements anywhere. The particles themselves do not communicate. The guiding wave does. This restores a kind of determinism, but requires accepting a non-local wave that violates the spirit of special relativity. Every interpretation struggles with non-locality. Either measurement causes instantaneous effects, or the wave function is non-local, or the universe splits, or hidden variables are non-local. There is no local realistic interpretation of quantum mechanics that matches experiments. Bell's theorem proves this. You must give up either locality or realism. Locality means effects propagate at or below light speed. Realism means particles have definite properties independent of measurement. Bell proved you cannot have both and reproduce quantum predictions. Nature has chosen, experiments have spoken, locality or realism must go. Most physicists sacrifice realism. They accept that particles do not have definite properties until measured. This preserves locality in a technical sense because entanglement cannot transmit information faster than light, but it requires accepting that reality is indeterminate, that measurement creates rather than reveals properties. This is a radical departure from classical physics, where objects have definite states whether observed or not. Some physicists sacrifice locality instead. They accept that particles have definite properties, but those properties are influenced by distant measurements instantaneously. This restores realism but requires faster than light influences. Special relativity is not violated because the influences cannot be used for communication, but the principle of locality is abandoned. Causes can have effects at arbitrary distances without delay. Either choice is disturbing. Either particles do not have definite properties, or distant events instantly affect local ones. Both options contradict intuition. Both suggest reality is fundamentally different from everyday experience. The EPR paradox was supposed to show that quantum mechanics is absurd. Instead, it showed that reality is absurd. Nature behaves in ways that seem impossible but are not. Entanglement is now used in technology. Quantum cryptography uses entangled particles to create unbreakable codes. Any attempt to intercept the particles disturbs the entanglement, revealing the eavesdropper. Quantum computers use entanglement to perform calculations impossible for classical computers. Entanglement is not a philosophical curiosity. It is a resource, a feature of nature that can be harnessed. But harnessing it does not make it less strange. Every application confirms that non-locality is real. The EPR paradox also connects to the measurement problem. If entangled particles are in superposition until measured, what causes collapse? If collapse is non-local, how does it propagate instantaneously? If collapse is not real, what explains the correlations? The measurement problem and the EPR paradox are two faces of the same mystery. Both arise from quantum mechanics predicting correlations that seem to require faster than light effects, or denying that particles have definite properties. Einstein was wrong about quantum mechanics being incomplete, but he was right to be disturbed. Quantum mechanics is complete in the sense that no hidden variables can reproduce its predictions while preserving locality and realism. But it is incomplete in the sense that it does not explain what is happening physically. The formalism works, the predictions are confirmed, but the ontology is opaque. What exists? What is real? What happens during measurement? Quantum mechanics does not say. It provides rules for calculating probabilities without specifying what those probabilities are probabilities of. The EPR paradox revealed that the universe is entangled at its core. Particles that interact become connected in ways that persist across space and time. This entanglement is delicate, easily destroyed by interaction with the environment. But it is fundamental. The universe is not a collection of independent objects. It is a web of correlations, a network of entanglements where distant parts remain connected through quantum links that transcend space. This web challenges the notion of separability. Classical physics treats objects as separate. Each object has its own properties independent of others. Quantum mechanics denies this. Entangled particles cannot be described separately. They form a single system. The whole is not reducible to parts. This holism is alien to classical thinking but essential to quantum mechanics. The universe is not made of independent pieces. It is made of relations. The EPR paradox forces a choice. Accept non-locality and reject classical separability, or accept that particles do not have properties until measured and reject classical realism, or accept many worlds and reject the uniqueness of outcomes. Every option requires abandoning a fundamental assumption about reality. Einstein hoped to show that quantum mechanics was wrong. Instead, he showed that reality is stranger than he imagined. The experiments vindicated quantum mechanics, and proved that nature operates according to principles that defy common sense. Spooky action at a distance is real. Entanglement is real. Non-locality is real. These are facts about the universe, confirmed by countless experiments. They are not interpretations or philosophical positions. They are how nature works. The EPR, Einstein refused to accept it. Nature does not care. But even non-locality is not the strangest implication of quantum mechanics and thermodynamics combined. The final paradox suggests you might not be real. You're sitting here reading this. You remember your past. You experience the present. You expect a future. But according to the laws of thermodynamics and cosmology, you are almost certainly not real. You are statistically more likely to be a disembodied brain that spontaneously fluctuated into existence 1 second ago, complete with false memories of a life you never lived. This is the Boltzmann brain paradox, and it threatens to destroy all of cosmology. The reasoning begins with thermodynamics. The second law states that entropy always increases in closed systems. Entropy measures disorder. The universe evolves from low entropy states to high entropy states. Order decays into chaos. Hot things cool. Concentrated energy disperses. Eventually, the universe reaches maximum entropy, a state of thermal equilibrium where nothing interesting happens. This is heat death, the ultimate fate of the cosmos if current models are correct. But thermal equilibrium is not static. It is a state of maximum disorder where particles move randomly. Occasionally, by pure chance, particles arrange themselves into low entropy configurations. A few molecules might spontaneously group together. A small region might become slightly cooler than average. These fluctuations are rare but inevitable given infinite time. The larger and more complex the fluctuation, the rarer it is, but nothing forbids it. Eventually any configuration will occur. This includes brains. A functioning human brain is a low-entropy structure. It contains organized matter, electrical patterns, chemical gradients. In a universe at thermal equilibrium, random fluctuations will occasionally produce brains. These Boltzmann brains pop into existence, fully formed with neural patterns that encode memories and thoughts. They exist for a moment, then dissolve back into chaos. But during that moment, they are conscious. They experience. They think they are real. Here is the problem. If the universe exists for infinite time at or near thermal equilibrium, Boltzmann brains will vastly outnumber normal brains. Normal brains like yours require entire planets, stars, galaxies. They require billions of years of cosmic evolution, star formation, planet formation, biological evolution. The entropy cost is enormous. Boltzmann brains require only a small random fluctuation. They are vastly more probable. Calculate the numbers. The probability of a random fluctuation producing a single brain is incomprehensibly small. But the probability of a fluctuation producing an entire observable universe with billions of galaxies and trillions of planets is incomparably smaller. If both are possible given infinite time, the smaller fluctuations dominate. For every real brain that evolves naturally, infinite Boltzmann brains fluctuate into existence. Therefore, if you are a randomly selected observer, you're almost certainly a Boltzmann brain. This conclusion is absurd but mathematically sound. If the universe spends most of its existence near thermal equilibrium, and if fluctuations occur randomly, then most observers are Boltzmann brains. You should expect to be one. You should expect your memories to be false, your surroundings to be illusions, your existence to be a 1-second fluctuation about to end. The fact that you have coherent experiences lasting longer than 1 second is evidence against this, but only weak evidence. A Boltzmann brain could fluctuate into existence with memories of a longer past. The memories are fake, but the brain does not know that. The paradox gets worse. If you are a Boltzmann brain, you have no reason to trust your memories or your reasoning. Your memories are random fluctuations. Your understanding of physics is a hallucination. The very argument that led you to conclude you are a Boltzmann brain is itself suspect because your brain is a random fluctuation. The paradox is self-defeating. If it is true, you cannot trust the reasoning that led to it. But if the reasoning is sound, the conclusion is probably true. This is a logical trap with no exit. The Boltzmann brain paradox threatens cosmology because it undermines all observations. If most observers are Boltzmann brains with false memories, then our scientific theories based on observations are likely wrong. We think we have measured the cosmic microwave background. We think we have observed distant galaxies. We think we have confirmed the Big Bang. But if we are Boltzmann brains, those observations are illusions. The data are hallucinations. Everything we think we know is false. Science becomes impossible because we cannot trust our own minds. Ludwig Boltzmann, who pioneered statistical mechanics in the 19th century, did not foresee this paradox. It emerged later from applying his ideas to cosmology. The paradox is named for him because it arises from Boltzmann's understanding of entropy and thermal fluctuations. The paradox shows that taking statistical mechanics seriously in an eternal universe leads to absurd conclusions. One way to avoid the paradox is to reject the eternal universe. If the universe has a finite past and will end in finite time, Boltzmann brains never dominate. There is not enough time for infinite fluctuations. The universe begins in a low entropy state at the Big Bang, evolves through structure formation, produces real observers like us, and eventually reaches heat death. Real observers exist during the era of structure. Boltzmann brains might appear later, but by then there are no real observers to compare them to. The paradox is avoided because the universe is not eternal. This solution requires explaining why the universe began in a low entropy state. Why did the Big Bang start with such low entropy? High entropy is vastly more probable. A universe beginning in thermal equilibrium is far more likely than one beginning in the highly organized state required for the Big Bang. The initial low entropy is itself a fine-tuning problem. The Boltzmann brain paradox is avoided but replaced with the question of why the universe started in such an improbable state. Inflation offers a partial answer. If inflation occurred, it erased pre-existing entropy and created a large low entropy region. The inflaton field drove exponential expansion, smoothing out irregularities and setting the stage for the Big Bang. But inflation itself requires specific initial conditions. Properties? The question is pushed back but not eliminated. Another approach is to argue that Boltzmann brains are not conscious. Maybe consciousness requires specific types of organization that random fluctuations cannot produce. A Boltzmann brain might have the physical structure of a brain, but without the right causal history it lacks subjective experience. This solution is speculative. We do not understand consciousness well enough to know what makes it possible. If consciousness is purely physical, determined by neural structure, then Boltzmann brains should be conscious. If consciousness requires something more, some continuity or causal history, then maybe they are not. But this is guessing. Some cosmologists take the paradox seriously as a constraint on cosmological models. Any model that predicts most observers are Boltzmann brains is wrong. This principle, sometimes called the Boltzmann brain problem, rules out certain versions of eternal inflation and cyclic cosmologies. If a model predicts the universe spends most of its time near thermal equilibrium, it predicts Boltzmann brains dominate, which we can reject because we observe a structured universe. Therefore, such models are incorrect. This approach treats the paradox as a reductio ad absurdum. Models that predict Boltzmann brain dominance are self-refuting. They predict that observers cannot trust their observations, but we do observe a structured universe with consistent laws. Therefore, models predicting Boltzmann brain dominance must be wrong. This rules out certain cosmologies without requiring a detailed understanding of consciousness or probability. Sean Carroll has argued extensively about Boltzmann brains. He points out that the paradox arises from taking the past hypothesis for granted. The past hypothesis is the assumption that, if you accept this, the universe evolves toward high entropy, and Boltzmann brains become probable in the far future. But if you do not accept the past hypothesis, if you allow the universe to have existed eternally in a high entropy state, then Boltzmann brains dominate in the past as well. The paradox becomes sharper. You should expect to be a Boltzmann brain now, not a real observer. Carroll argues that any viable cosmology must explain why the universe began with low entropy. The Boltzmann brain paradox shows that low entropy initial conditions are not just convenient for explaining structure, they are necessary to avoid the paradox. Without low entropy at the beginning, observers are overwhelmingly likely to be Boltzmann brains, which contradicts our observations. Therefore, the universe must have begun in a low entropy state. This is a constraint cosmology must satisfy. The paradox connects to the anthropic principle. We necessarily find ourselves in a universe where observers like us can exist. Boltzmann brain-dominated universes do not have coherent observers over long times. If most observers are Boltzmann brains, the universe appears chaotic and lawless to them. We observe a lawful structured universe. Therefore, we are not Boltzmann brains. We are typical observers in a universe where real observers exist. This selection effect explains why we should not worry about being Boltzmann brains despite the statistical argument. But this reasoning is circular. We conclude we are not Boltzmann brains because we observe structure. But Boltzmann brains could have false memories of observing structure. The observation itself does not distinguish real observers from Boltzmann brains. Both would perceive structure, one real and one illusory. The anthropic argument assumes we can trust our observations, which is exactly what the paradox questions. The Boltzmann brain paradox is not just a curiosity, it is a fundamental challenge to scientific realism. Science assumes we can trust observations and reasoning to build models of the universe. The paradox suggests that under certain cosmological models, this assumption is wrong. Most observers are deluded, their observations are hallucinations, their reasoning is based on false premises. If this is true, science cannot discover truth. It can only catalogue the delusions of Boltzmann brains. This is why cosmologists take the paradox seriously. It is not about whether you personally are a Boltzmann brain. It is about whether cosmological models are self-consistent. Models that predict most observers cannot trust their observations are defective. They undermine themselves. A good cosmological model must predict that typical observers are real and their observations are reliable. This is a non-trivial constraint. Many models fail it. The paradox also raises questions about probability in cosmology. How do you calculate the probability of being a certain type of observer? If infinitely many observers exist, both real and Boltzmann, how do you define typical? The measure problem in cosmology asks how to weight different outcomes in an infinite universe. Different measures give different answers about whether Boltzmann brains dominate. The paradox shows that getting the measure right is crucial. The wrong measure makes cosmology self-refuting. Ultimately, the Boltzmann brain paradox is a symptom of deeper issues. Why did the universe begin with low entropy? Why is there something rather than nothing? Why do the laws of physics allow structured complexity? These questions are not answered by current cosmology. The paradox exposes the gap. It shows that accepting the laws of thermodynamics and applying them to an eternal universe leads to absurdity. Therefore, either the universe is not eternal, or thermodynamics does not apply globally, or something else is wrong with our understanding. The paradox is uncomfortable because it cannot be dismissed. The reasoning is sound given standard assumptions. Fluctuations do occur in thermal equilibrium. Complex fluctuations are possible. If the universe exists long enough, Boltzmann brains will appear. The only escape is to modify the assumptions. Either the universe is finite or consciousness requires more than physical structure, or probability in cosmology works differently than we think. All options are controversial. None are fully developed. The paradox remains unresolved. You're almost certainly not a Boltzmann brain. But proving this requires assumptions about cosmology that we cannot fully justify. The paradox reveals how fragile our knowledge is. It shows that the universe's apparent order and our ability to understand it depend on special initial conditions we do not understand. The paradox is a reminder that the foundations of cosmology are not secure. We are building theories on assumptions that might be wrong, and if they are wrong, everything collapses. These paradoxes are not isolated, they are connected. Every paradox we have examined shares a common feature. They arise at the boundaries of our knowledge, where different theories meet and contradict each other. The information paradox sits where quantum mechanics meets general relativity. The measurement problem lives where quantum mechanics meets the classical world. The grandfather paradox emerges where causality meets space-time geometry. The fine-tuning problem appears where cosmology meets probability. The Fermi paradox connects biology to astronomy. Olber's paradox links the night sky to cosmic history. The horizon problem challenges inflation and causality. The twin paradox reveals relativity's counterintuitive nature. The EPR paradox exposes non-locality. The Boltzmann brain paradox threatens observational cosmology. None of these paradoxes exist in isolation. They form a network of cracks running through the foundation of physics. These cracks suggest something profound. Our theories are incomplete. Not wrong, but incomplete. General relativity works perfectly within its domain. Quantum mechanics works perfectly within its domain. But when the domains overlap, contradictions emerge. Black holes require both theories. The early universe requires both theories. Measurement bridges quantum and classical